Hey everybody. So what we're talking about today is the derivation of three different one-dimensional kinematics in physics. There's not a whole lot of things in physics that you should just sit down and memorize, but these three are worth it because anytime you're dealing with motion in one dimension, you're going to end up falling back on these three pretty frequently. So the first one we're going to talk about is v final equal to v initial plus acceleration times delta t. The second one we're going to talk about is v final squared equal to v initial squared plus 2 times acceleration times x minus x naught. And the third one we're going to talk about is the position equation, x equals x naught plus v naught t plus 1/2 at squared. So where do these come from? The first one comes from the definition of acceleration. That's this one right here, which is the definition of acceleration, dv dt, the time derivative of velocity. And that should make sense because your acceleration is your change in velocity per unit time. And what setting it up this way allows us to do is to say that a dt is equal to dv. In this step right here, there's more going on than is immediately apparent. The Leibniz notation of the derivative isn't actually a true ratio, so treating this like a fraction isn't always okay. But a lot of times in physics, it allows us to set up an integral, which is exactly what we're doing. And the integral that we're setting up is this one right here, which is a times the integral of dt from t1 to t2, which is equal to the integral of dv from v naught to v final. And actually, since we're already calling our original velocity v initial, I'm going to change v naught to vi. Okay, and you should remember from calculus that the integral of dx is just equal to x. So when we plug in the bounds, we see that both of these integrals just become the difference of their bounds. And we can show that a times t2 minus t1 is equal to v final minus v initial. And then if we switch out t2 minus t1 for delta t, just to make it one variable to work with and solve for v sub f, it's pretty easy to show that v final is equal to v initial plus, started to treat it as two variables again. It's equal to v initial plus a delta t. And that's where this first one right here comes from. The second one begins with the definition of average velocity. And in this video, we're just going to call that v bar. And average velocity is equal to v initial plus v final over 2. And that should make sense. The average of a number of measurements is the sum of the measurements divided by the number of measurements. So for an initial and final velocity, the sum of them over 2 makes sense for us. The second one that we're going to look at is position, which we've talked about being x minus x naught is equal to average velocity times delta t. And the reason we start here is so that we can say that delta t is equal to x minus x naught over v bar. And that's a good place to go, because what we can do from here is take this form of average velocity and stick it in right there. So then we show that delta t is equal to x minus x naught over v initial plus v final over 2. And so we divide it by a fraction, which is the same thing as multiplying by the fraction's inverse. So this is equal to 2 times x minus x naught over v initial plus v final. And then the second thing we're going to do after we set it up this way is we're just going to go ahead and flip both sides of this equation over. We're just going to take the inverse of each side. And the reason why will make sense in just a second is we're going to say that 1 over delta t is equal to v initial plus v final over 2 times x minus x naught. And the reason we've done this comes back to what we can say about acceleration, which is that it is equal to delta v delta t. And actually, we shouldn't set that up as a Leibniz notation. We'll go ahead and say this is acceleration is equal to v final minus v initial over delta t. There, that's a better form for this problem. And so what this shows us is that because this statement right here is equal to 1 over delta t, we can multiply it by v final minus v initial, and we have a statement that's equal to acceleration. So that's what we do, is we say that a is equal to v final minus v initial times v initial plus v final over 2 times x minus x naught. So you go right here, and you remember how foiling a polynomial works. You end up with a positive and a negative vf vi, and those cancel each other out, but you are left with a vf squared and a minus vi squared. So we find vf squared minus vi squared over 2 times x minus x naught. And remember that this is equal to acceleration. So from here, we're going to solve for v final squared. And we do that by multiplying acceleration by 2 times quantity x minus x naught and adding v initial squared. And we're able to show that v final squared is equal to v initial squared plus 2 times a times x minus x naught. So that's where our second one comes from. For our third one, we go back to the definition of velocity. Oh, sorry, I accidentally erased a little bit of that equation. I'll write it back in just a second. Let's see, that was v final equal to v initial plus a delta t. But this is the one that we're working on now, our position equation. And this goes back to the definition of velocity, like we were saying, which is dx dt. And we know from here that we show that velocity at a given moment is equal to initial velocity plus a delta t. So we can set dx dt equal to that statement and say dx dt equals v sub I plus a delta t. And then we use the exact same step to set up the integral that we used in the first derivation. And we say that dx equals v sub I dt plus a delta t dt. And then we're going to take an integral the same way. We pull out the initial velocity and the acceleration because they're constants, and the integral becomes v sub I times the integral of dt from t1 to t2 plus a times the integral of delta t dt from t1 to t2. And you remember going back to calculus, the integral of t dt is 1/2 t squared, and that's where we end up, is x, An equation is not an equation unless it is equal to something. So on the left side here we have integral of dx from x not to x. Sorry about that. But yeah, so when we take this integral, we have x minus x naught is equal to v times t2 minus t1 plus a times 1/2 delta t squared. And I actually shouldn't run in delta t in the same equation. We'll keep this consistent. We'll show that simplification one more step. T2 minus T1 squared. And then we can simplify this. And we can show that a position, x minus x naught, is equal to initial velocity times a change in time, delta t, plus 1/2 a, oh, I'm forgetting delta t's again, 1/2 a delta t squared. Cool. So I hope this was helpful, and if you tune in tomorrow, there will be a new video.